Hi, this is Charlie Zeiss with Stargate Pyramids and the Pyramid Science Foundation. Today's video is about high-speed aircraft, hypersonic vehicles, and Universal Phi Scaling. A few days ago, I did a video that linked Universal Phi Scaling with all of the major aircraft, jet aircraft that have ever been designed and produced around the world. And so I promised then that I was going to be doing a follow-up video on the higher speed aircraft, private aircraft, and in the background there you see the Russian version of the supersonic transport era of passenger flight as well that we had back in the 70s, 80s, and 90s up until the time that the Concorde was no longer allowed to fly in the United States and was ultimately scrapped. But we're going to be showing not only these aircraft, we're going to be looking at fighter aircraft and other military aircraft. And finally, we're going to be looking at hypersonic vehicles. I did a video on those earlier this year, but I want to look at it again with some additional information about the status of these programs and updates. So without further ado, let me open up the screen and we'll get started. So here's our thumbnail: Universal Phi Scaling in high-speed aircraft and hypersonic aircraft. Again, here's a picture. This is, again, the Russian version of this of a supersonic commercial aircraft airliner. But before we begin looking at the specifics, one of the things that I wanted to do was to give some basics as to why what we're talking about both in the previous video and this video is relevant to pyramids and to the organizing principles of the universe. So what we want to discuss today is, why is this important? Why is this geometry important in aircraft technology? And then we can certainly take that and apply it in other contexts. So I wanted to give everyone just a basic introduction to what's called laminar flow. And this first screen is just a very simplistic diagram of the difference between what's called laminar flow and turbulent flow. Now, in general, lamina means sheet, and so essentially what laminar flow does is any fluid mechanism, whether it be water or air or molasses, are all going to have these various characteristics. It's just that, and we can consider them all as fluids for purposes of discussion. The only difference between those three is going to be the viscosity of the three mediums. So what we discuss here is going to be equally as important. We're talking about water here, but it applies equally to air and to denser mediums, as I say, like molasses. So the top part of the screen shows you what's called laminar flow. Now, this is a diagram of water flowing through a pipe. And the idea here, as you can see, the arrows in the top part of the diagram, that portion of the water that's flowing through the central part of the pipe actually does flow faster than it does around the edges. And that's due to friction. The pipe is not perfectly smooth, and so there's a certain amount of adhesion that occurs due to the coarse layer of the inside of the pipe. And what that does is it slows down the rate of travel along the edges. Now, that issue becomes less and less severe as we go out into the middle of the pipe. And so as a result, what we find is that the flow of water is highest in the center of the pipe. Now, if we look at that in contrast to the turbulent flow diagram in the bottom, we see there that the flow is not consistent or laminar. It's not in a straight line. And that's due to both the, as we're going to find out, it can be due to a number of factors, but the speed of the flow of the water has a lot to do with that, as does the geometry, the friction in the pipe. And so you can see that different things can cause this turbulent flow. But what's the reason why we're talking about this? When you start to get turbulence in any medium, whether it's water or air, it's going to slow down the volume, the rate of speed of the object flowing through that medium or the medium itself. And therefore, we're going to have this turbulence. That turbulence with respect to aircraft in this example is going to mean lower speeds. It's going to mean higher fuel costs. And it's also going to generate more heat on the skin of the airplane. So to kind of get into a little bit more detail, one of the key equations that are used by engineers in the field of what's called fluid dynamics is what's called the Reynolds number. Now, the Reynolds number was developed in the 19th century, and we can express it as an equation. And don't get spooked here. We're going to explain this, and it's really pretty simple. RE equals rho VL divided by mu. And so in put that into English, RE is Reynolds number, rho equals density, V equals velocity, L equals length, and mu equals viscosity. So let's talk about those for a minute. The density of an object, the denser, denser is going to make the Reynolds number go higher. And we'll discuss the Reynolds number here in a minute, but let's just get the variables down. V is velocity, and again, L is length, and mu is viscosity. So let's talk about viscosity first, mu. If you're stirring something in molasses in a jar, if you were stirring a jar of molasses with a spoon, you wouldn't get much turbulence in that fluid relative to a glass of water because it's more viscous. And that tends to dampen the effects of turbulence. So you can see that that's an important factor in decreasing it. But things that increase turbulence include the density, the velocity, and the length. Now, for our discussions, the only variable that we're interested in is velocity, because we're measuring the velocity of an airplane. So for this purpose, but it could be the velocity of any object as well. So if the velocity as velocity increases, the Reynolds number is going to increase as well. And so now looking down below the equation, we state that the higher the Reynolds number, the higher the potential for turbulence. And higher turbulence will increase drag force. We'll talk about that in a minute, which slows the speed and increases the thermal energy or the heat that's produced on the skin of the object itself. And I didn't put it in here, but obviously a key factor here, it's going to increase fuel consumption as well. So engineers spend and aerospace companies spend millions, if not hundreds and maybe billions of dollars trying to minimize these turbulence effects in the design of aircraft, hypersonic vehicles, and the like. So the higher velocities associated, because we're going to talk about hypersonic travel here later, but the higher velocities associated with hypersonic travel present unique challenges because of the heat buildup on the skin of the vehicle. We'll talk about this a little bit later, but hypersonic vehicles, some of the failed tests of some of the US hypersonic vehicles about 12 years ago, the temperatures on those tests on the skin of the vehicle got up to 3,500 degrees, and literally it started peeling off, and the test flights, were not a success, but were a failure because of the heat generated on the skin of the hypersonic vehicles. The only other thing I would say here is the Reynolds number is only a general approximation of the potential for turbulence rather than laminar flow. Now, if we look at the diagram on the right-hand side, as I say, this is just a general approximation. Again, in general, if you have a number for the Reynolds number greater than 4,000, you're going to get turbulence, I believe, in all cases. If you look at the bottom, if the Reynolds number is under 2,300, in virtually all cases, you're going to get laminar flow. But in between, and you can see why this is just a rough approximation, anywhere between this 2,300 and 4,000 number is the kind of a transitional period, and you can either get turbulent or laminar flow depending upon a whole bunch of variables that are not contained in this equation. So to move on to a discussion of drag force, we were discussing a minute ago that airplanes can't go as fast if they're not aerodynamic. And so this is a discussion or formula, again, a generalized formula about drag force. And essentially, what we have FD drag force is equal to 1/2 of CD, which is defined as drag coefficient. And again, the same areas, density, velocity, and area. Now, all of these are going to be more or less constants for a given aircraft design. But the one thing that's most important is the drag coefficient. However, now to go down to the writing, engineers are not able, given current understandings and modeling, to make precise calculations of the drag coefficient. And the only way to do that is via wind tunnel testing or similar methods of measurement. Water tunnels, for example, for submarines or waterborne vehicles. However, what's interesting, we're seeing this in the air devices. I'm going to be doing another video on animals, or birds who fly, and we're going to see that even in airborne animals, that as well, that this geometry of universal Phi scaling always tends to minimize the drag coefficient, because we see it everywhere, not only in these airplanes, but in waterborne vehicles and waterborne animals as well. So what's interesting about this is that the principles of sacred geometry and the golden ratio are not taught in engineering programs. At least that's my understanding after having spent a lot of time trying to figure this out and talking to a number of engineers. But if anyone knows different, please get in contact with me so I can, restate this. But I have not been able to find any information linking sacred geometry to engineering or fluid dynamics, even though the golden ratio and universal Phi scaling are demonstrated to be important in the minimization of the drag coefficient in both air and water. So I just want to go through quickly. I'm going to turn on some music again so you don't have to listen to me for much longer until the end of the video when we discuss hypersonic vehicles. But I want you to see, again, the geometry of universal Phi scaling. The base angle, if you're thinking of the pyramids, is 76.345 degrees. The apex angle of that comes out to be 27.309 degrees. But I wanted to show you that you're going to find two separate angles, and that's why I wanted to do this quickly before we get started. You'll see that in many of these examples that the aircraft nose actually corresponds to half of that 27.309 degree angle, or 13.655. And I wanted to show you quickly why that is the case. If you'll notice, the geometry of this airplane is continuing to use that 27.309 angle along the bottom of the aircraft, as well as the top of the aircraft. So it's appropriate to use that 27.309 angle. However, in many aircraft, the bottom of the aircraft is perfectly flat. We'll talk about that. That's due almost exclusively to the use of what are called scramjet or ramjet engines, which are totally different in their functionality. And the air vents for those apparently will be, especially if they're underneath the aircraft, can be affected by the turbulence. So a lot of these aircraft are going to have flat bottoms. That's the best understanding that I have. But it's not going to be a surprise, or don't be surprised when you see the 13.655 angle as opposed to the 27.309 that we normally see. So with that, I'm going to stop talking for a while, and we can you can begin to listen to some music until we come back to talk about hypersonic vehicles. Well, one of the things that becomes obvious, having looked at all those slides and all those different examples, is that the world knows about this angle, but what I don't know, and I cannot seem to find any evidence of, is that they actually understand the universal phi scaling and the sacred geometry that's involved in this geometry, and its absolute significance in cutting down the drag coefficient for these planes. And of course, this does it just so much reinforces the model that George Leoniak and I put together on the organizing principles of the universe. It shows that the universe is infinitely fractal, so on and so forth. So now I want to get into, though, to the hypersonic vehicles. And in order to do that, I'm going to open up my screen again and get to that. Before we do too much more with this, I just want to say a couple of things. Uh, any number of countries are now in the process of developing hypersonic vehicles. I would, much prefer almost not to have to do this portion of the video, except that it demonstrates the significance of universal Phi scaling. But no one wants to see more missile systems, being brought upon the world stage. But one thing that's important, the three front runners in this currently are China, Russia, and the United States. And we are in third place. Russia has apparently used a number of Kinzhal missiles in the Ukrainian conflict, and we'll be seeing those in just a minute. China has successfully done a test flight in 2021, at least around the world, of a hypersonic, traveling around the world, of a hypersonic vehicle. It missed its target by some distance, but it was successful. But the United States systems are actually lagging the China's and Russia's. And unfortunately, given the state of affairs today, it would be wonderful to see the equivalent of a strategic arms limitation treaty on hypersonic vehicles, but I don't see that that's going to be forthcoming anytime soon, given the tensions between the three countries right now. But irrespective, you're going to find this geometry once again in all of these vehicles. And I'm going to be talking through this section because it bears some discussion. So here's the Kinzhal air launch system that has been developed by Russia and has been used in the Ukrainian conflict. I think it's interesting to see that, I mean, these are it requires a propulsion system to get them started. These have these ramjet, or in this case for hypersonic, scramjet engine technology that's involved. And you'll see the jet that's carrying the Kinzhal, the white missile underneath, has this geometry, but so does the Kinzhal missile itself. So Russia has used these, and they are in service in the Ukrainian conflict. Here's some examples of the Russian technology, excuse me, the Chinese technology. This is the WZ-8 hypersonic. This is an unmanned vehicle from China. This was put into service, I believe, in 2019. Here is an example of US technology. This is a Boeing scramjet demonstrator from 10 or 12 years ago. Now, this technology, we'll see some other examples of it in a few minutes, has largely been scrapped by the United States because of problems that we had about 10 years ago with the tests. Here's another example. This is the Dongfeng DF-17. This is a HGV, or hypersonic glide vehicle. This one was on display in 2019 in China, and I believe this is the one that they have successfully circumnavigated around the globe. Here's an example of a hypersonic glide vehicle that's under development in India. They believe that they will have this operational by 2025. And here is DARPA's, this is a picture of what is the prototype for the US technology. It's called the Falcon HTV-2. This is actually the system that has been scrapped. They've stopped testing on it, and the third version of this, the HTV-3, to my knowledge, has also been delayed as well. So we're not doing, we apparently are just not up to speed. I've demonstrated that this geometry is showing up in these vehicles, but I don't find it in the horizontal plane. And quite honestly, that could be part of the reason why these delivery systems aren't working as well as they could. I don't know any more specifics than that, but we do find the Universal Phi Scaling geometry in the Russian and the Chinese systems. So would take more research for me to make a definitive statement on that, but it's certainly something that would warrant some further consideration. And then finally, here is a SR-72 from Lockheed. This is under development and is estimated to be put into service in 2030. But this is a Lockheed prototype. And now you can see that the Universal Phi Scaling geometry is showing up, at least in the underside of this vehicle. So it may be that with an ability to incorporate, if they're not doing it already, the mechanics of Universal Phi Scaling into their design, that perhaps they could deal with the heat buildup issues more effectively. That would certainly require a lot more, detailed analysis to be able to confirm. But anyway, as you can tell, there are more than ample examples of Universal Phi Scaling in all of these high-speed aircraft. The ones that seem to work have historically used it, and the hypersonic vehicles that have been successful to date incorporated as well. So it's certainly demonstrating that this is a fundamental property and principle of fluid dynamics, which surprisingly, as I say, at least in the West, is not incorporated in, to my knowledge, in our engineering, curriculum. And probably, these principles we'd be served well if they were taught in our educational program. So I thank you all for watching, and you have a great day.